Imagine asking the simplest question in existence: how big is the universe? Somewhere perhaps there must be an answer, a number, a diameter, a final distance from one side of everything to the other. But what if the question itself is wrong? What if the universe does not have a size in the ordinary sense at all? Not because it is merely enormous and not because our telescopes are too weak, but because the idea of measuring the universe from the outside may be physically meaningless. That possibility is stranger than infinity. We are used to objects having boundaries. A house has walls, Earth has a surface. The solar system fades into interstellar space. Even the Milky Way, enormous as it is, has a measurable structure floating within a larger cosmos. So our minds naturally imagine the universe the same way, a gigantic sphere containing galaxies surrounded by something. But modern physics gives us no evidence for that picture. There may be no cosmic wall, no external darkness, no place where space suddenly stops. And according to general relativity, the geometry of the universe does not need an outside in which to exist. This is where physicists such as Leonard Susskind enter a territory that feels less like astronomy and more like a confrontation with the limits of human intuition. Susskind has spent much of his career studying the deepest relationship between space, gravity, quantum mechanics, horizons, and information. Again and again, those subjects lead toward the same unsettling lesson. Space is not necessarily the simple container we imagine it to be. Before asking how large the entire universe is, we have to separate it from the universe we can actually see. The observable universe is finite. Light does not travel infinitely fast, and the cosmos has a finite age. The universe has been evolving for about 8 billion years, so there has only been a limited amount of time for signals to reach us. Yet because space itself has expanded while that light was traveling, the most distant regions we can observe today are much farther away than 8 billion light years. The observable universe is roughly 93 billion light years across. That number sounds like the answer to our question. It isn't. It tells us the approximate diameter of the region from which light or other signals have had enough time to influence us. It does not tell us the diameter of everything that exists. Imagine standing in the middle of a thick fog with a lantern. You can see only a limited distance. The circle of visibility around you has a measurable radius, but that does not mean the world ends where the fog becomes opaque. Your horizon describes the limit of your information, not necessarily the limit of reality. Cosmology confronts us with a similar horizon, and there is something even more disturbing about it. An observer in a galaxy billions of light years away would have their own observable universe centered on them. Their cosmic horizon would not perfectly match ours. They would see regions forever inaccessible to us, while some regions visible to us might be inaccessible to them. There is no evidence that Earth occupies the true center of the universe. Every observer sees themselves near the center of their own observable region because light reaches each observer from all directions. The center moves with the observer. That alone should make us suspicious of any mental picture showing the universe as a glowing ball with Earth somewhere inside it. The observable universe is not necessarily a physical object with a surface. It is a region defined by causal contact. But perhaps you might think, beyond our horizon there is still some final boundary. Maybe the total universe is simply much larger. That is possible. But it is not the only possibility. The total universe could be finite. It could also be spatially infinite. Current observations tell us that the large-scale geometry of the observable universe is very close to spatially flat. In ordinary Euclidean geometry, parallel lines remain parallel, and the angles of a triangle add to 180 degrees. Cosmologists test cosmic geometry using patterns in the cosmic microwave background, the distribution of galaxies, gravitational lensing, and other measurements. So far, the observable universe looks remarkably close to flat. A perfectly flat universe can extend infinitely, but flatness alone does not prove infinity. The topology of space could be more complicated. A universe can be finite without possessing an edge, and that is where everyday intuition begins to fail. Imagine an ant living on the surface of Earth. The ant can walk north, south, east, or west. If it continues far enough in the right direction, it can eventually return to its starting point. Yet at no moment does the ant encounter the edge of Earth's surface. The surface is finite. It has a measurable area, but it has no boundary. Now remove one dimension from your imagination, and then add it back in mathematically. Our three-dimensional space could, in principle, possess a global geometry that is finite yet unbounded. Traveling far enough in one direction might eventually bring you back, depending on the universe's topology. That does not mean cosmologists have discovered that this is the actual shape of the universe. They have not. It means physics allows geometries that demolish the assumption that finite things must have edges. Albert Einstein's general theory of relativity made this possible because gravity, in Einstein's description, is not simply a force acting inside space. Matter and energy affect the geometry of space-time itself. Space can curve. Time can distort. Distances can evolve. The stage is no longer separate from the actors. And once geometry becomes dynamical, asking what the universe is expanding into becomes dangerously misleading. This is one of the most common questions in cosmology. If the universe is expanding, what is outside it? What is it expanding into? The answer given by standard cosmology is that expansion does not require an external empty space. On large scales, the distances between gravitationally unbound regions increase as the cosmic scale factor grows. Galaxies are not necessarily racing outward through a pre-existing void from one central explosion point. Rather, the geometry describing distances between distant regions changes with time. Every analogy fails eventually, but consider dots drawn on the surface of an inflating balloon. As the balloon expands, every dot sees most other dots moving farther away. No dot on the surface needs to be the center of the expansion. But the balloon analogy contains a trap. A real balloon expands into three-dimensional air. The universe does not need to do that. The balloon's external room exists only to help our brains visualize a changing geometry. In general relativity, the geometry can be described intrinsically, from within. There may be no external cosmic room at all. Leonard Suskind's work becomes especially relevant when we push this idea toward horizons. For decades, Susskind was one of the central figures in the black hole information debate. Stephen Hawking's calculations had suggested that black holes radiate and can eventually evaporate. That raised a terrifying possibility. If information about everything falling into a black hole disappeared completely, quantum mechanics might be violated. Susskind strongly resisted that conclusion. The struggle eventually led to ideas such as black hole complementarity and helped motivate the holographic principle, an extraordinary proposal associated especially with Gerard Hooft and Susskind. The holographic principle suggests in broad terms that the information describing a region containing gravity may be encoded on a lower dimensional boundary. This is not merely science fiction speculation. In certain theoretical settings, particularly through the AD-SCFT correspondence discovered by Juan Maldacena, holographic descriptions have become precise mathematical tools. But our actual universe is not straightforwardly anti-de Sitter space. So applying holography directly to cosmology remains an active and difficult area of theoretical research. Still, the lesson is profound. Volume may not be as fundamental as it appears. The space inside a region may emerge from information encoded in a radically different way. And now the original question begins to mutate. If space itself is emergent, what exactly are we measuring when we ask for the size of the universe? Susskind and other theorists have explored the possibility that space-time geometry is deeply connected to quantum information and entanglement. In modern theoretical physics, this connection has become one of the most fascinating clues toward quantum gravity. Entanglement links quantum systems in ways that cannot be described by ordinary classical independence. In some theoretical models, changing entanglement changes the geometry associated with space-time. This does not mean physicists have proved that our universe is literally made of entanglement. But it raises an astonishing possibility. Distance itself may not be fundamental. Two locations may seem far apart because of the structure of an underlying quantum state. If that idea is even partly correct, then asking for the ultimate size of reality may resemble asking for the physical width of a relationship. The measurement assumes the thing being measured is fundamental. It may not be. And cosmology gives us another reason to doubt our instincts. Inflation. The leading modern picture of the very early universe includes a period of extremely rapid accelerated expansion known as cosmic inflation. Inflation was developed to address puzzles, including why the universe appears so spatially flat and why distant regions of the cosmos have remarkably similar properties. There is significant observational evidence consistent with important predictions of inflation, especially the pattern of primordial fluctuations reflected in the cosmic microwave background. But the detailed mechanism of inflation remains uncertain. Physicists do not yet know which, if any, specific inflationary model describes nature. Some versions of inflation lead to something more radical, eternal inflation. In eternal inflation, inflation ends in some regions while continuing elsewhere, potentially producing enormous numbers of causally separated regions, sometimes described as pocket universes or bubble universes. Leonard Susskind became deeply involved in thinking about the implications of this possibility, particularly in connection with the string theory landscape. String theory does not appear to produce only one possible low-energy universe. Instead, its mathematics may allow an immense landscape of possible vacuum states, each associated with different physical properties. Combined with eternal inflation, this inspired one of the most controversial pictures in modern cosmology, a multiverse in which different regions realize different effective laws or constants of physics. This remains speculative. There is no direct observational confirmation that other pocket universes exist. But if some form of eternal inflation is correct, the idea of assigning one meaningful global size to the cosmos becomes even more problematic. The universe might not simply be larger than what we see. Its total structure could be beyond any finite scale we normally imagine. And there is a bizarre consequence. In an infinite universe, with sufficiently uniform statistical conditions, extremely unlikely arrangements of matter may occur somewhere simply because there are infinitely many opportunities. There could, in principle, be regions resembling ours at extraordinary distances. Not because of magic, because infinity behaves in ways the human brain was never designed to handle. Yet cosmologists must be careful here. Claims about exact duplicates depend on assumptions about the number of possible states, cosmological conditions, and how infinity is treated. They are not established observations. Infinity is mathematically simple to write down and physically treacherous to interpret. This is why saying the universe is infinite is not the same as knowing it is infinite. We do not currently know. And perhaps the most unsettling fact is that we may never know from direct observation. Cosmic horizons are not merely technological obstacles. Some are fundamental. Because the expansion of the universe is accelerating, driven by what we call dark energy, sufficiently distant galaxies can become permanently causally inaccessible. Light they emit in the distant future may never reach us. There are regions of reality from which no future message can arrive. No telescope can solve that. No civilization, however advanced, can simply build a larger antenna and overcome the causal structure of space-time. The universe hides information not only because we are primitive, but because geometry itself creates limits. This was one of the great lessons of black hole physics as well. A black hole has an event horizon, a boundary beyond which signals cannot escape to a distant observer. Cosmological horizons are different in important ways, but they share a haunting feature. They divide what can influence an observer from what cannot. For Susskind, horizons are not just boundaries in space. They force physics to confront questions about information, entropy, and what an observer is actually capable of knowing. The black hole information problem taught physicists that asking what exists may sometimes be inseparable from asking what can be observed and how information is encoded. Cosmology pushes that tension to the scale of everything. Suppose the universe is truly infinite. Then no observer can measure its total extent. There is no outer marker, no final galaxy, no last meter of space. But suppose instead that the universe is finite and unbounded. Then a total volume might exist mathematically while still having no edge and no external perspective from which someone could stand back and measure it like a planet. Either way, the picture of the universe as an object sitting somewhere begins to collapse, because somewhere is already part of the universe. Where is the universe located? The question may have no physical meaning. Location describes a relationship between things within space. If space-time includes the entire physical arena, asking for its address demands a second arena outside the first. Then we could ask where that arena is located, and another after that. The question creates an infinite regress because our language quietly assumes an external viewpoint nature may not provide. The same problem appears when people ask what happened before the Big Bang. In some cosmological models, the question may be meaningful. In others, time itself behaves in ways that make an ordinary before impossible or undefined. Physics has not settled the ultimate origin of the universe. But general relativity already teaches us that space and time are physical structures, not eternal containers guaranteed to exist independently of everything else. This is what makes the universe so difficult to imagine. Evolution trained us to judge distance at human scales. We understand 10 meters because we can walk it. We understand 1,000 kilometers because maps shrink it. Even a light year can be turned into a number. But cosmology asks the mind to understand something for which there may be no outside, no center, no edge, and perhaps no total measurable extent. And then quantum gravity asks whether space itself is fundamental. Susskind's career sits at the center of that collision between intuition and mathematics. String theory replaces point-like particles at its basic perturbative level with tiny extended strings whose different vibrational patterns correspond to different particles. It naturally includes a quantum excitation behaving like the graviton, which is one reason the theory became a major candidate for unifying gravity with quantum mechanics. But string theory also suggests that the space-time we experience may be only one manifestation of a deeper mathematical structure. Holography pushes the idea further. A gravitational universe in one description can, in some cases, be mathematically equivalent to a non-gravitational quantum theory in fewer dimensions. Two radically different pictures can describe the same physics. So which picture is real? Perhaps that question is also too simple. If two descriptions contain precisely the same observable information, physics may refuse to privilege the one that feels more intuitive to us. Space can be deep in one description and encoded differently in another. Distance can look fundamental from one perspective and emergent from another. A volume can contain a black hole, while its information behaves as though the boundary matters more than the interior. The universe keeps taking concepts that seem obvious and turning them into questions. Size, distance, inside, outside, beginning, edge. These words work beautifully in ordinary life because ordinary life occupies a tiny, calm corner of reality. At cosmic and quantum scales, they start to fracture. Tonight, if you look into the sky, nearly every visible point of light belongs to our local cosmic neighborhood. Beyond naked eye vision are hundreds of billions of galaxies within the observable cosmos, spread through an expanding web of matter and dark matter. Behind the farthest galaxies we can observe lies the ancient glow of the cosmic microwave background. And beyond the regions from which light has reached us, physics does not reveal a wall. Our equations simply continue describing possibilities. Perhaps space continues far beyond our horizon, perhaps forever. Perhaps it closes on itself through a topology so enormous that no repeated pattern is visible within our observable region. Perhaps inflation created a structure whose full scale cannot meaningfully be compressed into a single number. Perhaps a future theory of quantum gravity will reveal that asking for the universe's size is like asking how many miles wide a dream is, a question built from concepts that cease to apply at the deepest level. We know the size of our observable horizon with remarkable precision. We know the universe is expanding. We know the large-scale geometry we can measure is close to flat. We do not know the total spatial extent of everything. And those statements must never be confused. Science becomes most powerful, not when it turns uncertainty into certainty, but when it discovers exactly where certainty ends. So there may never be a moment when humanity writes one final number on a blackboard and announces the diameter of reality. The deeper discovery may be that reality was never an object waiting to be measured from the outside. We are inside the geometry we are trying to understand, built from the same quantum fields, governed by the same space-time, limited by the same horizons. Every ruler we construct exists within the thing we are attempting to measure. Every telescope looks outward while remaining trapped inside its own causal region. And every theory that tries to describe the whole universe is itself being created by a small arrangement of matter somewhere within that universe. Perhaps that is the strangest scale of all. A universe vast enough to contain horizons we can never cross has produced minds capable of realizing those horizons exist. And if space itself eventually turns out to emerge from something deeper, then somewhere beneath galaxies, black holes, strings, and quantum information lies an even more unsettling question. Not how big is the universe, but what is it that we have been calling space in the first place?